Hello, welcome to your lesson on kinematics. This is our third lesson, because way back when we studied differentiation, we looked at kinematics. Now we are looking at it in a deeper way. We're going to include integration, and we will also include trigonometric functions. Let's get rolling. We're going to flash back first to remind us what kinematics is all about. Kinematics is all about motion. Alright, so let's say an object followed this purple path from point A to point B. If we said, what is the distance traveled by that object, we can just find the distance along that path. That's our distance. However, an important thing in kinematics is, well, what if we just measured the actual direct distance from A to B? That is called displacement. And in this case, we have positive displacement because it's to the right. So displacement is that direct distance from point A to B, and the actual distance is the path you've taken, whether you're straying to and from the object. All right, let's take a look. Further on, we said position function can be represented with s of t usually. And this is an example of a position function. We can see an object begins here, and over time, let's assume this axis is time, t, then the object over time gets further from its initial position and then back closer to its initial position. All right, so over time it moves away and back towards. Now, if we found the slope of the position function, the slope is actually a rate, and in this case a rate is a velocity. So if we took the derivative of this function, we get the velocity function, and the velocity function represents the velocity at any point in time here. So as we can see, the velocity is positive velocity, because it's moving away from the starting point, but it's a decreasing positive velocity, right? There's less slope, less slope, less slope, and here at the peak there's no slope. So right here the object actually has zero velocity, and now it has negative slope, means negative velocity. That means it's returning back to its starting place. So velocity has a direction. It can be positive or negative. And here is our velocity function graphed, and we can see exactly what I just described. There are positive values of velocity here, large positive values, because we have a large slope here to begin, large velocity. And then there's decreasing velocity values, smaller slope values, until we get to here. There's no slope, and here we see no velocity because of the y value of 0. And then after that there's increasing negative values for velocity, and that's what we see here. Small negative velocity, and then more increasing negative velocity. Alright, then you take the derivative of this again, you get a new function, and that is now our acceleration function. In this case, the derivative of this is -2. And acceleration can be graphed like this. Acceleration explains what is happening to velocity for every moment in time. So in our case, velocity is decreasing by 2 meters per second, you could say, if this was meters and seconds. 2 meters per second every second. All right, so in other words, if the velocity was 10 to begin, 1 second later it would be 8, another second later it would be 6, and so on, and then eventually the velocity would be becoming negative. So this is how much velocity is changing. All right, with those reminders, we're ready to look at something else we've looked at before, and we'll take it a step further in just a moment. So let's say we have a sprinter, and their position is represented by this function. So we have a position function here, s of t. All right. That function can be represented here. So I see the red function is that position function. And you can see the runner goes from a small velocity, speeds up, then there's slope, and then slowing. You can see slightly slowing down at the end until they reach about 100 meters. So this is a 100-meter sprint. Now, if I put a line here, you may notice, if you look very carefully, that until that line the slope is increasing. They're increasing their velocity, and after that line the slope is slightly decreasing on and on from there. So that's what we see on the blue curve here, which is the velocity function, and we can see the 3 functions here. So the velocity function looks like this. We have positive velocity, it's increasing, they're increasing their speed until they get to here, there's a peak. And that's the highest velocity this runner gets, and then after that it's decreasing velocity. It's still positive, but it's decreasing. See, decreasing. All right, and the green line here is our acceleration function right here. And we can see, since velocity is increasing, the acceleration is positive, but it's increasing at a decreasing rate. Okay, so the acceleration is like the slope of the velocity graph, and we can see the slope is positive, but decreasing positive until there's no acceleration here. And that's what we see here, positive acceleration until there's no acceleration, and then negative acceleration, which is actually deceleration. He's slowing down right here. All right, hope that brings you back to what position, velocity, acceleration, what kinematics is all about. Let's jump ahead now. So let's say we have the motion of another particle. and it's given by this position function here, and this says it's between 0 and 7 for t values, where t is seconds and s is meters, and this only applies again between time equals 0 and 7. Okay, this is called a motion diagram. It shows you the motion of this particle. So we can see the particle begins at time 0, and even at time 0 it is already 3 meters away from some kind of reference point here. So it begins, it goes in this direction, and at some unknown time at 55 meters from that initial location, it turns back. It heads back towards there. And then again, at some unknown time, it turns around again and starts moving away again until at 7 seconds, it is here, some number of meters that we don't know away from this starting point here. So that's a motion diagram. It shows the direction of travel. All right, let's use that and compare it to a graph. So here's a graph of the position function as well. So this s of t function has been graphed here, and we can see again at time 0, it is 3 meters already beyond some reference point, and then it's going away from it, and that's what we can see here, moving away from it until at time, well, here we have the time. Here we don't see it labeled, but here we see it clearly. At time 2, it is 55 meters away right here. And at that point, it turns back and starts heading back towards 0 here. So it's heading back. And okay, so it is heading back, and then at 5 seconds, it is now a distance of 28 meters from that beginning point here, and we can see that that must be happening right here. So we know that this is now time 5, and we also know this is a distance of 28. And then it turns around again and starts moving away from here again, away, and it's going away, away, away until I don't even see up to 7 here, but it's moving away here, and we can see that happening here. All right, so the motion diagram matches what we see on the graph. Let's take that information and move forward. So here's what we're going to solve first. Number 1, here's that motion diagram, and here's the graph again. Let's answer these questions. Number 1, find the velocity function for the moving object. What would be the velocity? So we know here's the position function, and you know the velocity is the derivative. So what is it? Well, velocity is the derivative of the position function, therefore this. So check your work. Hopefully you have the same one. Great. All right, next question. Find the values of the following constants, which are shown in the motion diagram, right? All those numbers, or sorry, all those variables we have on there, P, M, N, and Q, we're going to find the values. And yes, we saw them on the diagram, on the graph. But let's say we didn't have the graph and we had to solve this just algebraically. How do we begin? So P is this point here. Well, that is the position of the particle at time equals 7. That means you can just put 7 into the position function and solve it. So try that now. 7 goes in there, and we get this, which works out to this. So double check yours, but now we know at 7 seconds, we didn't see it on the graph here, but at 7 seconds, the particle reaches a distance of 80 meters from the beginning here. Great, next question. Find M and N, and those are those time values. We already know from here that they are 2 and 5, but how would we solve them using the equations we have? So we want to know the times when the object changes direction. And a hint I'll give you here is, we know the object changes direction when, well, we talked about this, what is the slope of this represented by? Well, the slope is represented by the velocity, right? So here's positive velocity, no velocity, and then negative velocity. So we know it changes direction at the moments when there is no velocity, because it's changing from positive to negative or negative to positive velocity. So find the points when there's no velocity. All right, to do that, we set the velocity function equal to 0, and there is our velocity function setting equal to 0. Solve that. When we solve that, we can, first I divided by 6 to make it easier to factor. I factored it like this, and then you can find t equals 2 and 5, which means m must be 2 and 5. All right, and that matches what we saw in the graph here. All right, let's try C. In C, we're looking for Q, the displacement of the object from the origin at n seconds. So the displacement at n seconds. Well, we just found out that n is equal to 5, so that means we're putting 5 into the position function, because that tells us the displacement or where the object is. Put that in there and solve. So that works out to 28 meters, and again, that is basically the value Q. We were just looking for Q, we found it, it's right here. And again, that matches what we saw in the graph here. we had at 5 seconds, it was 28 meters away from the beginning, which is the displacement, right? But that's not the distance the object has gone, because the distance is actually up here and then down to here. But the displacement is just from there to its current position, so 28. All right, great questions. Let's keep going. Next thing we're going to look at is this question. All right, so we have our position function, and we found the velocity function as well. So now my question to you is, what does the integral of the velocity function represent? Well, the answer to that is kind of simple. We know when we take an integral of something, we go back, we jump back. And if we, to go from s of t to v of t, we took the derivative, so now going backwards, taking the integral of the velocity brings us back to the position function, st. In other words, the integral of vt is st. All right, so st to vt is the derivative, but vt to st is the integral. All right, that's important to know. Easy idea, but also really important. Okay, so next question. Therefore, what will the result of this definite integral be? All right, so now we've put boundaries on this integral. So what would that represent? And think back to what we just wrote here, right? Okay, let's take a look. So that, if we did it by what we know about integration, we would take the integral of v of t, which we just talked about produces the position function, and now our boundaries are 0 to 7. So that means we're substituting 7 in there and subtracting 0 substituted in there. So what does that mean? What does that represent? Well, that would be the displacement from time 0 to time 7, right? By doing this, you're finding how far the object went from a beginning time of 0 to a beginning time of 7, and that can let us figure that out. So let's calculate that. What should that be? Okay, when you calculate, oh, that's interesting, I'm repeating that. When you calculate those, first of all, it might be helpful to have our things here. This was 3, this was a distance of 28, which we calculated before, and this was a distance of 80. So with those three values there, we can move forward with this a little bit. So s of 7 we know is 80. That's the position of the particle at time 7. S of 0 is at 3. So what is the difference between those? Well, the difference between those is 77. That means the object has a displacement of 77 from here to 7. So from beginning of its motion to end of its motion, it has a total displacement of 77. And we can confirm that on the graph. Let me go back to the graph for a second. I think it's important to see it together. On the graph, we can see it began here, time 0, and it was 3 meters away from some reference point. And from there to the end, which again we don't see, but 7 is 80, we know it goes from there and directly up would be 77 meters to get to the end point. And we don't worry that it went up and down, because we're not talking about distance, we're talking about displacement, so how much it went in total. So that's a really key idea here. Let's go back to that. When we take the integral like that, we are actually finding the displacement. Okay, so when we take a definite integral of velocity, we are finding the displacement between those times, and the times can be anything. It doesn't have to be 0, it could be any time. All right, next question. Is finding this definite integral then the same as finding the distance traveled? Well, I hope based on what we just talked about, you're saying no way, can't be. No, because the distance is the total distance gone, right? So we can see again the displacement on here as well. From 3 to the ending point here, you go from 3 to 80 is 77. That's the displacement. But the distance would be like this, back again, and back again. So the distance traveled would be 52, because from 3 to 55 we go 52 meters. And then for some reason they turned around, but anyway, turn around and go back 27 meters to get to 28. And then from there go forward 52 more meters to get to the end here. So our total distance would be the addition of those three numbers, which is 131 meters. So that's the distance. This is the displacement. Make sure you know the difference. It's very important. And again, displacement can be found by taking the definite integral of velocity, but distance cannot. So how are we going to find the distance then? Let's take a look at that. So now try this on your calculator, and we're going to try this in just a moment. All right, as you may remember when we did integration, if we take the definite integral like this, and there's areas above and below the axis, it counts the ones below the axis as negative values. And that's why this gives us displacement. We'll see a diagram of that in just a second. This gives us displacement, but now if we put an absolute value around that, it basically says we're going to turn all these pieces that are under the axis into positive pieces, and therefore it'll add up all the all the distances together with no negatives applied, so it'll give you the total distance. Well, let's try. So let's put this on our calculator and see how it works. So just to remind us how to do it on our calculator, we're going to do the math button to get an integral. And then if you go down the list a little bit, you'll see integral down there. There it is, number 9. So number 9 is our function, integral function. In there, I'm going to put 0 to 7. Those are our bounds of integration. 0 seconds to 7 seconds, our velocity function. Okay, so I have the velocity function here. We're going to enter that here. 6x squared, and then minus 42x plus 60. And then in the end, we have to put integral in terms of x, so dx right here. Okay, I'm going to run that. Let's see what we get. Look at that, 77. I just ran the integral without the absolute value. But what if we run it with the absolute value? Because without the absolute value, notice I'm just running this. It gave us 77 is what we saw here. All right, but now with the absolute value, so let me set that up as well. If you don't remember how to get the absolute value in here, I set up the integral here again, 0 to 7, but I want absolute value like we see here. Absolute value means we're turning all the negative values positive, right? So press math again, then arrow over to number, and the first one there you see is ABS, that's absolute value. So I'm going to press number 1, there's my absolute value. Now I'm going to enter the same function here again, 6x squared, and so on. All right, there I've entered it. You can see the absolute value around that. I'm going to press enter. Let's see what that integral gives us. Just taking a moment to run. Interesting. All right, let's see what we get. All right, here we go. I'm surprised it took so long, but 131. So it matches what we found here for distance. So let's talk about that one more time. It's really important to see. When I ran this integral in the calculator, it gave us 77. It gave us the displacement because that includes this and then subtracts this value and then adds this value. It takes away the negative values. Whereas when we put the absolute value, it doesn't consider negative and positive velocities. It makes all velocities positive. So velocities are always positive, therefore all the values are positive, and you're just adding up this, and that's what we did here when we found the distance. So remember that, important. All right, let's summarize those key ideas by looking at some diagrams here, or some graphs. So here is the first one we found, the integral, definite integral of the velocity function. Remember, when there's no absolute value there, that represents the displacement because we have positive and negative values all affected there. So that's the displacement from t equals 0 to 7. The graph that goes with that looks like this. So notice this is no longer the position graph. This is now the velocity function graph, okay? So if you look at the velocity function, it has a positive velocity, then a negative velocity. That's that portion between 2 and 5 seconds when the particle was going backwards. And then it has positive velocity again. So if the function goes like that, and we run an integral on it, we are finding the combination of these three areas. Right? Because when we do an integral, we're finding the area under a curve, or area between a curve and the axis, actually, right? So that's what that integral will give us. It will give us those three areas combined. But remember, when an integral calculates area beneath a curve, it counts this as a negative value. So really, you'll have area 1 minus area 2 plus area 3. And that's why the integral of this gives us the displacement, because it actually subtracts that part from the motion of the particle, because the particle went back a little bit and then forward again, and that negative is subtracted from our total distance traveled. Now, in contrast to that, we ran an integral like this with an absolute value now of the velocity function. What that will do to our graph is, so that shows us our distance from time equals 0 to 7. And that graph will look like this. Basically, when we run an absolute value on any function, we get rid of all the negative y values of that graph. So here is the graph, and notice that this part of the parabola has been reflected over the x-axis and now is here. So all y values have been made positive. We can see the same parabola, but it just stays here. So this time when we run that integral, right here, we are actually combining the three areas, and they're all three positive numbers. So that's why that gives us our total distance traveled, because it doesn't matter if we're traveling to the right and then left and right again, it counts all that as our total distance traveled. And that's what's going on here in terms of the calculus. We're finding the positive area. All right, good to know. Really interesting stuff. Hope you see those connections as being really fantastic. Let's keep moving. So now use the ideas we've just learned to answer this question. Here is the velocity function. This is not the position function. This is the velocity function of some particle. So notice it has positive velocity, then a steady positive velocity, then a decreasing positive velocity, and negative velocity, and on and on. All right, so find the particle's displacement and the distance traveled. Exactly the two things we just talked about, right? So what is the displacement and what is the distance traveled? And we don't have any functions here, so this is not about functions. This is going back to the idea of just area under graphs, right? So the area under the velocity graph, just like we had here, the area under the velocity graph gives us either the displacement or the distance. So try it here. What would be the displacement? I'll give you a hint to start. Well, the displacement we just learned is the integral of the velocity, so the integral of this function, which means the area under this function. And here we're talking from 0 to 11. And in this case, we're going to be adding this area, subtracting this one, and adding this third area here. So this is our first area, a trapezoid. And in case you forgot, the area of a trapezoid is given by this equation. And A and B are our two base lengths. All right, and then this is going to be our second shape right here, a triangle. And then there's going to be another triangle here. So find the displacement geometrically by using the areas there. What's it going to be? Okay, check your work here. The area of the trapezoid is here, minus the area of this triangle because it's underneath the axis, right? And then plus the area of this triangle right here. And that gives us our displacement of 10.5. And remember, displacement, the negative values are subtracted, so we see the subtraction. All right, try the same thing now, but now we're looking for the distance traveled by this object. So for distance, we take the integral, but the integral of the absolute value of the velocity. That means this time we are adding the 3. We're taking the absolute value. That means even this negative one is turned positive. So what's it going to be? In this case, if we're adding the 3 areas, the total is 19.5 meters. All right, I hope that problem here brings this idea of areas and integrals and velocities. All this stuff is coming together into a big conceptual understanding for you. So just so we see here, what did this absolute value do to this graph? Well, again, any negative portions are reflected over the axis. So you can see this portion here can be reflected up, and now it is here. So when we find distance, we're finding those 3 positive areas added together. All right, try this one out. We have a particle moving along a straight line and between times 0 to 5, and we want to know the velocity of the particle. So here's our position function. What's the velocity function? And then once you know the velocity function, find out when the particle is moving to the right and when it is moving to the left. I'll give you a hint with that one as well. When we have the velocity, remember it's moving in one direction, then the velocity becomes 0, and then it moves in another direction. So find the velocity, set it equals 0, and then find out what's happening on either side of those points when the velocity is 0. Okay, so let's check. Here's our velocity function. I'm setting it equal to 0, and I solved an answer of 2. That means at time 2, this particle has no velocity. So I'm going to put 2 here. I'm going to put velocity here. I'm going to see what's the velocity before time equals 2 and what's the velocity after. So put any t value less than 2 into the velocity function. What do you get here, positive or negative? Well, it's negative. How about here? Put any t value greater than 2. It's positive. So that means the velocity is negative and then positive. So that means, and we assume in these problems that when we see positive velocity, the particle is moving to the right, and we see negative, it's moving left. So we can say it's moving left between 0 and 2, and it's moving right between 2 and 5, because we know that's the end point of this journey here. Okay, next question. Draw a motion diagram. Well, give it a try. Remember, the motion diagram shows when the particle is moving left and right, and we just figured that out. And then you also have to mark what are those times and distances covered by the object as it gets to these turning points. So let's see how you do. So check yours here. The particle we know first is actually moving left. So it begins at time 0, and then this has a value of 3 here. You're like, okay, how do I know that's 3? Well, into your position function, you're like, the important times in this journey are time 0, time 2 when it changes direction, and time 5, which is the end. So you take those 3 values, 0, 2, and 5, you put them into your position function, and you figure out where is the particle located at each time. At time 0, if you put 0 into here, you get a value of 3. And then at time 2, -1, and at time 5, 8. So it begins here, time 0, at position 3. Then it goes left, because we figured that out. It arrives at time 2, and now it is -1 from whatever this reference point is. And then it changes direction, moves right, until time 5, when it is now at a position at 8 meters, I guess meters, I'm assuming here, yep, meters, I think, yep. So 8 meters away from this reference point 0. Okay, that's how you draw a position diagram. Make sure you remind yourself. Next, write definite integrals for the particle's displacement on the interval 0 to 5 and for the distance traveled. So again, we're coming back to this displacement and distance traveled. So what's it going to be? And then it says use your GDC. So don't worry about calculating them by hand. Just use your calculator to calculate each of the displacement and distance. Okay, now check your work. Displacement again is the integral, and the distance is the definite integral. The same function we're putting in here, it's our velocity function, right? And you get an answer of 5 and 13. You can confirm on your calculator. All right, now it's time to bring calculus, trigonometry, and kinematics together. And this is certainly going to be lots of fun. So let's keep going. I have some problems for you here. All right, just a reminder, when you're tackling questions in kinematics, when we see the word initially, it means time equals 0. When we see at rest, that means an object has no velocity, velocity equals 0. When it's moving right or up, we say velocity is greater than 0, positive. When velocity is positive, it's moving either right or up. When it's moving left or down, velocity is less than 0, it's negative. And when velocity and acceleration have the same sign, an object is speeding up. When they have different signs, it is slowing down. And the reason for that is if something has a positive velocity and then a positive acceleration, it means the acceleration is adding to the velocity. So the velocity is increasing. That means it's speeding up. And likewise, if you have a positive velocity but a negative acceleration, then the acceleration is acting against the velocity, making it become smaller and smaller. Okay, let's take a look. Here's a problem. We have a similar problem we just did, but now our position function is given in terms of a trigonometric equation right here. So find the particle's velocity and acceleration at any time t. So that just means find the v function and the a function. Okay, let's see if you were able to do that. There it is. We just took the derivative of that. So remind yourself, if you didn't get these answers, try again. How do you take the derivative of that? Don't forget to do chain rule here with that 2. And then acceleration would be the derivative of this to here. Double check your work with sine and cosine derivatives if you can get that. Okay, next question. Find the particle's initial displacement, velocity, and acceleration. Okay, now you have the 3 functions. So initial means time is 0. So all that means is you're putting time 0 into all 3 functions, and you found the initial position, velocity, and acceleration. Next step, find when the particle is at rest. That means velocity is 0. And then determine when it is moving right or left on this interval. So first we're going to set the velocity equal to 0 and solve this equation. Now this, you notice we have 2t here, so we should change the domain we're looking at. If this becomes 2t, everything's multiplied by 2 like this. So on that domain, what are the solutions of this? Okay, now check your work. We have these 2 solutions. So now we're going to check the velocity, and here's the 2 times we found when there's no velocity. So before that, the velocity is either positive or negative. So we're going to check here, here, and here. Take a value less than this, put it into your velocity function, and do you get a positive or negative value? Negative, then positive, then negative. That tells you velocity is negative, then positive, then negative. Okay. Alrighty, what this tells us then is that here's a negative velocity, positive, negative. Therefore, it is moving left from 0 to pi over 4. It is also moving left from 3 pi over 4 to pi, which is the end of our domain here, and it is moving right from pi over 4 to 3 pi over 4, because movement to the right is always when velocity is positive. All right, let's go. We have one more to look at in this problem, and it is this. We are looking for the displacement of the particle after pi seconds. Remember, displacement, we can take the integral of the velocity function, right, for displacement. And if it says after pi seconds, it means from 0 to pi seconds. Okay, so run that integral and see what you get. Let's check our work. So here's the integral of the velocity function from 0 to pi. Check all your work with the integral. from 0 to pi. It's a definite integral, and we get an answer of 0. Interesting. So this is telling us from 0 to pi seconds, the end result is like the particle hasn't moved at all. So let's take a look at a graph of that to see what's going on here. So here's a graph of the initial position function. This is s of t graphed here. Notice the particle begins here. When time is 0, it is at a position of 4 meters from whatever this point is. Then it went closer to that point, away from that point, closer to the point. It's following a sine curve, so it's moving along that curve. And notice here after pi seconds, which is right here, pi seconds, it is right here. So how much has it moved from the beginning? Well, nothing. The end result, it is the same distance of 4 meters from whatever reference point this is. It's the same distance, 4 meters. So it's like it's gone away, it's gone towards it, away from it, but ended up coming back to where it started. So the displacement is 0. However, and you may have been thinking this, and a lot of students who are thinking deeply about this think this very same thing now. They think, wait a minute, why did we just take the integral? Doesn't this function here tell us the position? So if we're talking about the displacement, can't we just put in pi into this equation and figure out the displacement of the particle? Because isn't this what this equation is all about? Well, let's not make that mistake. If you put pi into here, you would actually get a value of 4. That's because if you put pi in here, it's not your displacement, it is your position at time pi. So you would get a value of 4. That's your position. But then you would say, well, okay, well, the position is 4, so it's 4 away from the starting place. But the point here is the starting place isn't always 0. The starting place in this case is already 4 meters away from 0. So to apply this formula and find how much the displacement is, you could do this. You could say s of pi minus s of 0. That's saying what is its position at pi, what is its position at 0, and subtract those two. And if you put pi in here, you get 4. If you put 0 in here, you get 4. And 4 minus, right? So positions 4 and positions 4. And when you subtract those, you get 0, which is the same as we got here, the displacement. So know that displacement can be found using the integral, but also know that we can just check the difference between the positions, beginning and end. All right, next thing here. Last problem, I promise. I know this video is quite long. So read this here. We have a particle. Here is its velocity function. And it says when time equals 0, the displacement of the particle from a fixed origin is 5 meters. Find the expression for s in terms of t. So we're beginning with the velocity function and we need the s of t function. So how are you going to go from velocity to s of t function? Well, we're going to take the integral. So try that now and see what you get. Okay, so take the integral of the velocity function. This integral is going to require substitution. All right, great topic we just looked at. So let's apply it here. I'm going to set u equal to cosine of t because I know the derivative of that is negative sine t, and I see a sine here. So I know I can make a substitution in just a moment. However, I see this negative, so I'm going to bring that negative to this side so that I can substitute for that sine t directly with this. And of course that 4 can be pulled out of the integral. So now with the substitution made, we have this. That 4 was pulled out. There's the negative sign. There is u squared because we have cosine t squared, and then the du dx. That simplifies to this. Now we can take the integral of this. The integral of that is 1 over 3, and this becomes a 3, but 1 over 3 and the 4 become negative 4/3, and plus c, because this is not a definite integral. So now we have this. But that's not our position function. We can't have c in there. We need a value there. Well, that's precisely why we were given 0 and 5. It's telling us a coordinate on this position function. When time is 0, the distance is 5, or the position is 5. So this is our position function. Why don't you substitute that coordinate in here and solve for c? Okay, let's do that. So, oh, sorry, I put the cosine back in there. Don't forget to do that, of course. And now put that point in there. So that point goes back in there. And we get this. So 5 is our position, and that position occurs when time is 0. Solve this, and c is 19 over 3. Therefore, our position function is this full thing here, and now we have 19 over 3 here. Notice how all this work we've been doing for a good month and a bit, or 2 months even, it's all coming together. Integrals, trigonometry, calculus, everything. It's all together now. All right. One last thing with this problem. So now we have the position function and velocity function. So find an expression for the acceleration. All right. And then Find the acceleration, velocity, and speed of the particle when time equals 6. Okay, check your work here. Acceleration is the derivative of velocity, so here is the derivative of this velocity function. Notice that we have a function times a function, therefore we need product rule to do that derivative. Check your work carefully for the product rule. There's a lot happening there. There's our acceleration function. And now acceleration at 6, velocity at 6, and don't forget that speed is the same thing as velocity, but speed does not have a direction. So all we do is take the absolute value of velocity and we get this. And final one here, D and E. Determine whether the particle is speeding up or slowing down when time equals 6. Remember, if velocity and acceleration have the same sign, if they're both positive or both negative, then it is speeding up. And finally, find the displacement of the particle and the distance traveled over this interval. So now we're applying the integrals again. Okay, here's your answer for D and the explanation here. And here's your answer for E, displacement and distance. And you can calculate that using your calculator. Don't worry about working that one out by hand because they're quite complex. Great job. Quite the lesson you had here. If you hung in there for the whole video, congratulations. I hope you have a great understanding of this topic, which really does bring together so much of our content. So great job. See you soon.